Good morning, everybody, and warmly welcome to the GN course on stellar pulsation, probing the interior of stars. This course will consist of a series of lectures and tutorials in which the theory of stellar pulsation will be discussed together with its implications on our knowledge on stellar structure and evolution and the implications for astrophysics in general. The first question which arises is, why should we deal with this subject? And for a theoretician, the motivation by observations is the best thing to motivate and to justify the deal with this subject. So the observation tell us that some stars, and if not all stars, are variable. This variability may show up either photometrically, that means in terms of the light curves these objects have, or spectroscopically in the way the spectral lines vary with time. Well, the question then arises: where do these variabilities come from? What is the origin of the variability? And there are many causes of variabilities in stars, and one very obvious cause of variability are eclipses, for instance, in binaries. Well, this is a common effect, and this is not what we would call a pulsation in the sense we would like to study. Essentially all binary systems show variability simply by the motion of the two companions around each other, and eclipses may be one of the manifestations of this binarity in stars. If the stars get closer, for instance, in symbiotic stars, we will have also variability, which we would not call eclipse, but which is a variability which is caused by the interaction of close binaries. These are then symbiotic stars. Another variability which arises is once in a binary system, one component sheds mass on its companion and forms, this gas streaming from one companion to the other forms an accretion disk or a disk. In this case, we also have a variety of variability which are usually caused or which are termed as cataclysmic variables. Also, this kind of variability is not what we would address as stellar pulsation. Then another class of variable stars are novae and supernovae. In these cases, the variability is caused by an eruptive, more or less variable or more or less periodic eruptions in case of novae, and in the case of supernovae, it's just a single event. In these cases, nuclear reactions and nuclear explosions are the cause of variability. Also, these eruptive or explosive variability is not what we would call stellar pulsations. Finally, there are stars which have spots, like our Sun, and if these spots, which are darker than the stellar surface, rotate around the star, we will get a variability. This case of variability due to star spots is also not what we mean by pulsation. These star spots require magnetic fields for their existence, so we will also exclude magnetic fields as the origin of stellar variability. So the last class of cause of variability are the pulsations, and these pulsations are properties, or may be regarded as intrinsic properties of stars. So we may arrive then to exclude all these other origins of stellar variability. We arrive at a definition what we mean by stellar pulsations. Of course, this is only a first approximation and needs to be refined in the course of this lecture series. Well, so we would like to define as a first approximation stellar pulsation as an intrinsic property of a single isolated star. So no binarity is involved here, and the pulsation is an intrinsic property of a essentially non-magnetic, non-rotating single star. This variability may manifest itself either in a single period variability, or it might become as a multiple periodic variability. Even a chaotic variability can be addressed as a pulsation of a isolated star. This variability may affect the effective temperature, may affect the radius and the luminosity of the star. Okay, so, concerning the history of pulsation, the hypothesis that variability of a star might be an intrinsic property and might be addressed as a pulsation was put forward first by Shapley in 1940 on the observational side, and it was considered on the theoretical point with a theoretical point of view by Eddington in 1918. So the pulsation hypothesis is about more than 100 years old. At this stage, I would like to recommend for further reading and intensive reading parallel to this lecture series, an article by Ledoux and Walraven from 1958, or the monographs by Cox, Theory of Stellar Pulsations of 1980, and a more recent book by Uno et al., Non-Radial Oscillations of Stars. These are books which might be helpful in further reading, parallel or in extension to this lecture series. Well, the next question which we have to answer is, well, it might be interesting in itself to consider stellar pulsations as a phenomenon and to study this phenomenon in a theoretical background. But of course, it would be highly desirable to get more motivations for the study of this subject, and in fact, it is much more important. Stellar pulsations are much more important for astrophysics rather than just looking for the phenomenon itself, because when stellar pulsations are a very, very useful tool to determine distances by using pulsating stars. So pulsating stars are distance indicators, may be used to determine distances in astrophysics, one of the very basic tasks which have been done by astronomers, and the prominent group of stars which can be used to measure distances are the classical pulsators, the Cepheids. Well, in addition to determine distances, stellar pulsations might also be used to determine stellar parameters, to confine the range of stellar parameters directly without reference to the spectrum of the star, but using the additional informations of periods, measured periods, and the ratio of periods. In some cases we have more than one pulsation periods, and then we can also use period period ratios to determine and confine stellar parameters such as masses and densities, for instance. And which is an active field of study now, is that we can get direct information from the pulsation, from the spectrum of pulsation frequencies on stellar interiors and stellar structure, and also on stellar evolution. This is the very active field of helioseismology and astroseismology. In this field, we can directly look into the star, which we cannot do using the electromagnetic spectrum. The pulsation periods, measured pulsation periods, give direct information on the structure, for instance, the stratification of densities, pressures, and temperatures. So this is a motivation, a further motivation to study stellar pulsations, not only motivated by the phenomenon itself. Distance determination of stellar parameters, and gaining some insight into the structure and evolution of stars. So let us consider one of the prominent pulsators. The classical pulsator is the star Delta Cephei, and the group of stars which behave similar to Delta Cephei are called the Cepheids. There is also a star Beta Cephei, which is also variable, and one has to be careful to distinguish between the Beta Cepheids and the Delta Cepheids. Usually the Cepheids are the Delta Cepheids, and if Beta Cepheid stars are meant, then they are called the Beta Cepheids. All the variable stars are named after one of their prominent members. So the Delta Scuti variables, for instance, are named after their prominent member Delta Scuti, or Ara Lyrae variables are stars which behave like their prototype Ara Lyrae. So Cepheids, the main importance for astrophysics is that Cepheids are used as distance indicators, and the prototype Delta Cephei, which we will discuss in detail now. Well, the period of Cepheids ranges between 1 and 50 days. So this is accessible for human beings. These are periods which we can measure in our lifetime. The Delta Cepheids are very bright stars, so we can see it in very in large distances. So because they have luminosities between 300 luminosities and 3 times 10 to 4 luminosities, so they can be seen in large distances. That makes them particularly useful for distance as distance indicators. Their radii range between 14 and 200 solar radii, and their mass lies between 3 and 14 solar masses. The change of luminosity or change in brightness is usually a little bit smaller than 0.1 magnitudes, and the range or the variation in velocity seen by spectral line variations lies between 30 and 100 kilometers per second. Spectral type of these Cepheids lies between F5 and G5. Why are these Cepheids so important for distance measurements? This comes from the fact that for these Cepheids there is a relation between their absolute visual magnitude and the period of their pulsation. This period was first found in 1912 experimentally and phenomenologically, and this experimentally this relation is given by absolute visual magnitude is minus 2.8 times log period in days minus 1.43. Theoreticians like to express this relation in terms of the luminosity rather than the absolute visual magnitude, and this relation in terms of the luminosity of the star is given by log. Luminosity in solar units is 1.15 times log the period in days plus 2.47. Well, let us have a look how this period luminosity relation looks like. This is the experimental relation between the visual magnitude and the logarithm of the period in days. And you see there is a linear in these variables. There seems to be a linear relation between the absolute visual magnitude and the period in days. The scatter of this relation, which is seen here, is not of statistical origin, but this is an intrinsic scatter because the Cepheids form the Cepheids. The variable Cepheids form a strip in the HR diagram which has a finite width, and within this strip, of course, there is an intrinsic scatter, and this intrinsic scatter is seen in the period luminosity relation. So this is an intrinsic scatter. There is a finite width of this period luminosity relation, which comes from the fact that the Cepheids have occupy a strip of finite width in the Hertzsprung-Russell diagram. Okay, so this strip in the HR diagram is shown in this picture. We have an HR diagram where the absolute visual magnitude is plotted as a function of the spectral type or the effective temperature down here. The hot stars on the left side, the red stars are on the right side here. Here we have this main sequence, and here is the position of our sun. The Cepheids occupy a strip which is indicated in red here. So the Cepheids are the hatched region here. These are the delta Cepheids, the classical Cepheids, which occupied a strip of finite width in the HR diagram. There are not only the delta Cepheids in this diagram, there are also other stars like W Virginis stars, there are R Lyrae stars, there are delta Scuti variables, and even if you go to the extension of this instability strip towards the white dwarf regimes, you will find variable white dwarfs in the extension of this instability strip down here. So what you see here is this strip has a finite width, so we expect a finite width also in the period luminosity relation. Well, you see also here the periods of indicated, which corresponds to the lower end of the Cepheid instability strip, and also at the upper end. So here at low luminosities, we have a period around 1 day, and at the upper end we have a period of about 50 days for the delta Cepheid variables. What you also see from this diagram, there are other variable stars in the HR diagram. There are red stars, red giants, which are variable. There are also groups of stars at the hot end, which are the beta Cepheid variables here. Well, it seems that at least part of the HR diagram is filled with variable stars. And, well, you may perhaps know that also our sun is found to be variable. We don't see it, but if you investigate the surface of our sun, you will find that our sun pulsates with a period around 5 minutes. That means, or this might give rise to the suspicion that more or less all stars seem to pulsate, and that we can cover the entire HR diagram with pulsating stars, maybe it's just a matter of observational techniques, of observational refinements, that we in the end we will find almost any star to pulsate. Okay, so that's about that's what we want to say about. Well, perhaps I should mention here again another class which is not shown in this diagram, which is found at the upper end here of the diagram, which are the so-called luminous blue variables. They are not covered in this diagram, but these are also stars which are strongly variable and which we will address in the course of this lecture series as well. Okay. So, well, now let's go and consider the star delta Cephei in detail. Well, I promised that not only the pulsating variables cannot only be used for distance determination, but they can also be used to determine stellar parameter. And I will show in the next few minutes how, in fact, stellar radii can be determined using the so-called Bade-Wesseling method, which is based on the fact that our star pulsates. And as an example, we will discuss the star delta Cephei himself. Okay, what is the idea behind this Bade-Wesseling method to determine the stellar radius once the star is pulsating? Well, what one has to observe is light curves, that means the luminosity or the brightness of the star in different colors, and simultaneously take a spectrum and determining the radial velocity. So what we do is observe light curves in different filters, and we take a spectrum simultaneously and determine the variation of the radial velocity by the shift of spectral lines. Well, we take delta Cephei as an example. So let's consider the light curve of delta Cephei here in the visual band. Delta Cephei has a period of 5.366 days, and what is given here as a function of the phase of the pulsation. So this interval denotes the phase of the pulsation. We see here the light curve. Well, it is not a nice trigonometric function. It looks like a sawtooth profile. This is the light curve of delta Cephei in one of the filters, or in one of the wavelength ranges. Parallel to it, we have the radial velocity curves. Well, I should say here this scale is with an arbitrary 0 point, because delta Cephei is not as bright as 2.2 or 2.4 or 2.8 here. It's a star of between third and fourth magnitude. So the 0 point here is arbitrary of this plot. So second plot would be the radial velocity determined from spectral line variations. Well, what we see here is if we take the symmetry axis of this radial velocity curve, we will see that the symmetry axis to which the radial velocity curve is symmetric to lies by minus about 15 kilometers per second. The question is, what is this due to? Well, a minus sign means that the star comes towards us. This is the convention for determining the sign of the radial velocity. This means that there is a systemic velocity of delta Cephei. Delta Cephei, this star has radial velocity or comes towards us with a velocity of around 15 kilometers per second. The rest of this curve is the variation with respect to the center of mass of delta Cephei. Okay, so if negative sign means the star comes towards us, then this will denote the photosphere of delta Cephei approaching us, and this part means that the photosphere moves away from us. That means that in this case, once the relative velocity or the relative velocity with respect to the center of mass of delta Cephei is 0, then this should correspond to the maximum radius. This is once the velocity changes from approaching us to going away from us. This means this is a maximum radius, and of course, then this point would be the minimum radius. If we compare this maximum radius and the minimum radius with the light curve, then we will find that the maximum radius is, or the minimum, let's consider the minimum radius is appearing before the maximum luminosity is reached. So if we have if we work with the hypothesis that once the star is compressed or is at its minimum radius, it should be hotter because it's compressed. Like for instance, if you compress a gas, then it will have the maximum temperature and the maximum compression phase. This is not true because the phase of when the star is hottest comes after, is slightly shifted with respect to the minimum radius. This effect can be understood, but it has been a long time a matter of discussion. But meanwhile, it is understood by radiative transfer processes in this object. Okay, so this is the situation for a well-studied radial velocity curve and light curve for the star delta Cephei. Okay, so what is the idea to determine the radii using radial velocity curves and light curves together? Well, the Bade-Wesselink method consists of two steps. The first step is we choose 2 points along the light curves which have the same color. Same color means they have the same effective temperature. So what we do, we take light curves in different wavelength band, and then we subtract these light curves or take the differences between these light curves to obtain the color, and we take 2 points where the color, 2 points at the color curves which have the same color. That means the same effective temperature. What we do then is we determine the difference of the volumetric magnitudes at these points. Let's denote these points with 1 and 2. And let's determine the volumetric. In the ideal case, it should be the volumetric magnitude. It is certainly difficult to determine volumetric magnitudes sometimes. So one might take also the difference of visual magnitudes at these points where the color is the same. Well, we know that the star satisfies Stefan Boltzmann's law. That means the luminosity is equal to radius squared or proportional to radius squared times the 4th power of the effective temperature. Or, yeah, well, what it means, if we have points of same color, then we have points where the effective temperature is identical. And once we determine then the difference or the ratio of the luminosity at these points, that means we determine the difference of bolometric magnitudes, then we can get hold of the ratio of the radius. Well, bolometric magnitude is defined or is connected to the luminosity by the relation bolometric magnitude is minus 2.5 log L plus a constant. Then the difference in bolometric magnitude at some point of the light curve is minus 2.5 logarithm of the ratio of the luminosity at 0.2 divided by the luminosity L1. Of course, the differences of bolometric or any other magnitude is distance independent. This is, of course, very nice to have a measure which is for which we do not have to know the distance in detail. So this is a precise and exact relation. The delta M bolometric is giving us the logarithm of the ratio of the luminosities at 0.2 and 1. Okay, and if we now know that the effective temperature, taking the Stefan Boltzmann law, if we now know that the effective temperatures at 0.1 and 2 are identical, this means that delta M bolometric is minus 2.5 times log of R2 squared over R1 squared. Any other quantity cancels. So that means we get from this difference in bolometric magnitude at 0.1 and 2, we get the ratio of radii. The question is now, how do we get the radii themselves? Well, in order to get the radii themselves, we make use of the radial velocity curves, in particular between the points 1 and 2. That means we integrate the radial velocity curve with time. Well, we know the time derivative of the radius is given by the radial velocity, d by dt of the radius minus the measured radial velocity. So the radius differences between point 1 and 2 is the time integral from time t1 to time 2 over the radial velocity curve times dt. The radial velocity curve is known, and the integral can be performed on the basis of the observational data. And this means we get, by integrating the radial velocity curve, we get the difference in difference of radii. Once we have the ratio of the radii and the difference of the radii, we have the radii. Sometimes the Bade-Wesseling method is or a modification of the Bade-Wesseling method is used only on the basis of the radial velocity curves. In the same way as described here, one takes the radial velocity curves and one gets the difference of radii simply by integration of the radial velocity curves. And if then our Cepheid is close enough to ourselves, and we can measure with the biggest telescopes available using interferometric method the change in angular diameter of our star, then we can, using the change of angular diameter together with the difference in radii, simply to determine the radii themselves. Okay, so in that case, this is also called the Bade-Wesseling method. In that case, we can using interferometry and this part of the Bade-Wesseling method, we can also determine the radii the radii of a Cepheid without having to resort to the light curves. Okay? So there is an alternative or a modification of the Bade-Wesseling method using only the radial velocity curves, but together with a measurement of the change of the apparent diameter of the star once the Cepheid is close enough, and we can, using interferometric method, determine the change of angular diameter. So to finish with the discussion of the Bade-Wesseling method, let us consider the strategy using some instructive graphs here. So what we measure is the light curve of the star in different wavelength bands, indicated here with mj, where j means, or it should indicate the wavelength band in which we observe. We take differences between the different wavelength bands, and we end up with color curves Cij. This should denote the color curves, the variation of color of the star. Now we pick, this is the idea of the Bade-Wesseling method, 2 points along the color curves which have the equal color, same color, and we measure then the difference of brightness at these 2 points of equal color, determine the difference in magnitude between these 2 points, 2 and 1. And according to the relation we found before, this difference then for points of equal color give us the ratio of the 2 radii. Then we have simultaneously observed the radial velocity curve, which is symmetrized along the line to which the radial velocity curve is symmetric to. Here are the 2 points, 1 and 2, which correspond to the same color. Then we integrate this curve with respect to time and get the radius as a function of time, and then we can determine at these 2 points the difference in radii. This is the radius here, the difference is the difference in radii. So we have difference in radii and we have the ratio of the 2 radii, so we have the radii themselves. So this is an example for the measurement of a stellar parameter using a pulsating star. This would not have been possible without the fact that the star is pulsating, and so the pulsating stars should serve as an example that pulsating stars may be used to determine stellar parameters directly. The next chapter we would have to open is now to consider what determines the pulsation periods of the star. May I remind you, the star Delta Cephei has a period of 5.366 days. Other stars in the HR diagram have periods shorter, and some stars have periods which are even longer. So along the Delta Cephei regime, we have periods between 1 and 50 days, and if we go down to white dwarfs, we have periods of seconds. So the next question which has to be addressed, and which we will address in the next lecture, will be how or which facts or which parameters will determine the pulsation period of stars. So this will be done in the next lecture.